with an email, and then we'll share it with you. Yeah,
Perfect. Thanks
no
a lot.
worries.
Yeah, okay, let's start. I'm a little bit sick, so I hope I'm going to talk clearly enough. But of course, if you have any remarks or something that wasn't clear, please ask me afterwards, or you can even send me an email. So yeah, let's start. So this presentation, as you already saw in the description, is going to be about insight in active inference. So modeling aha moment, which is just another term for insights, in a modified Wisconsin card sorting task using active inference. So just a little bit of the context to start. I am a newcomer in the field. I am originally trained in engineering, specialized in physics, and I just did recently a master's in artificial intelligence. But active inference, I actually just got to know it from a random podcast where Carl Friston was there talking about active inference. That's actually what got me very interested in it. And so currently, I'm in the process of writing a PhD proposal of 4 year with Hans, who is also in the meeting as my supervisor. And we are basically interested in the aha moments, also referred to as insight in the framework of active inference. So specifically what we want to test is we want to test a hypothesis that is whether insight is the result of a reduction in model complexity. So this hypothesis, I first encountered it in Friston and colleagues 2017, where there was an artificial agent that was simulated and a Bayesian model reduction that was simulated as well. And also afterwards by Lokonen and colleagues in 2023, who did a extensive description of insight in the framework of predictive coding and active inference. So if you look at the definition of insights, a basic one would be the sudden appearance of an idea or solution into consciousness. And it seems like it's fundamentally different from analytical problem solving, from regular problem solving. But the question is, how exactly? So if you look at the phenomenology of insights, you see that there are many characteristics that actually come out. So for example, the fact that it's sudden, it's a discrete phenomenon, the fact that it's accompanied by a burst of confidence and positive emotions, the fact that it often requires restructuring, sometimes impasse, and then on average, it seems that it's more accurate than regular problem solving, etc., etc. But if you look at those characteristics, what is actually unique to insight? And it seems like among those ones, two seem very fundamental. So the fact that it's sudden and the fact that it's accompanied by a burst of confidence. And so now the question becomes, how can we explain those two characteristics in the framework of active inference? And before that, let's just illustrate those characteristics. So if you look at those two graphs that come from actually experimental data, you see on the left, you can imagine now that you're playing a game and that you can indicate your closeness to solution, for example, with a slider. On the left, you see that you came to the solution progressively. And on the right, you see that you came to the solution very fast, suddenly. And if you look at the self-reported insight versus non-insight, you see that usually on the left, this is a typical trajectory of non-insight. And on the right, this is a typical trajectory of insight. So just like that, you can see the discrete nature of insights regarding analytical problem solving. And then the second characteristic, which is the burst of confidence, of course, you cannot see it in the graph, but if you ask or if you measure confidence, you'll see also that its insight is usually accompanied by a more intense feeling of confidence. So now the question is, what are the mechanisms behind? So there's been over a century of research on insights, extensive phenomenological description, but there's a lack of mechanisms. What are actually the principles, mechanisms that underlie insights, and how are they fundamentally different from other kind of problem solving? So if you remember, the hypothesis that we want to test is whether insight is the result of a reduction in model complexity. In order to kind of illustrate that statement, let's take the following image. So you probably already saw it, but let's pretend that you didn't if you already did. So here, if I ask you, for example, to find something in the image, something hidden, in the beginning, because the image is kind of ambiguous, it's not salient, there's going to be many competitive alternative hypotheses that are going to compete with each other, and that's going to be a high uncertainty state. And so you will start looking at different point of the image, doing some visual saccade, trying to resolve that uncertainty in order to find the percept that is hidden in the image. Maybe after a while, you realize that there's actually a dog in the image. And so all of a sudden, the hypothesis that it was a dog in the image is way more likely, is much higher than the others. And so here, something that you can do is remove the alternative hypothesis because they are basically redundant. And so if you do that, you will essentially carry a complexity reduction. And that, in principle, will lead to aha moments. It was the dog all along. And that complexity reduction, if you remember the free energy, you can write it as complexity minus accuracy. And therefore, if you can reduce the complexity while still trying to keep the accuracy high enough, that will reduce in a net free energy reduction, and therefore that will be consistent with the free energy principle. Now, if we go back to the characteristic of insights, there was the discreteness and there was the burst of confidence. So how can we explain those two characteristics in the framework of active inference? Well, the first one, obviously, model reduction is a discrete phenomenon. So it wouldn't be too surprising that insight happens suddenly. The second one is maybe a little more complex, is that model reduction will lead to an increase in efficiency of inference. You know that it's the dog. There's a decrease in uncertainty over policies because you know where to look, you know how to interpret the image, you know that there's a dog in the image. That will therefore lead to an increase in expected precision, which will lead to a phasic dopamine response, and therefore a burst of confidence. So those two characteristics, of course, are essential to insight, but we can even extrapolate. We can, for example, talk about the fact that insight can even happen in periods of incubation. Without any new data, you're in your shower, you're in your bed at night, you think about a problem, and then all of a sudden, aha, the solution came up. And so, of course, this is also consistent with the hypothesis because model reduction is done in the absence of new data. It is done offline. And then one last informal statement is that oftentimes insight is related to a clearing of one's mind, which also makes sense because model reduction is about removing redundant connections and selecting the simplest model that is consistent with the data. And therefore, it makes sense that it will feel like your mind got cleared. So if you want to model this, of course, in active inference, we need to choose a task to model and to try to simulate that insight experience. So what tasks should we choose? Well, one of them, the most popular one that is used here now in the literature, is the compound remote associate task. And so here the goal is to find a new word that is best associated with three presented words. So for example, imagine that I give you man, glue, and star, and you need to find a fourth one that is associated with all three. You think, you think, you think, you can even report your closeness to solution, and all of a sudden, you realize that it's, for example, super. And this is might be resulting in aha moments. So if you look, for example, at how a trial would look like, an experimental trial, you can see the following illustration. So you have the three words. You can, for example, report your closeness to solution with a slider, where you indicate how close you are to the solution. You think about it. When you get the answer, you press the space bar, you type your solution, and then you can report your confidence. You can report the intensity of the aha moment if you had one, and then the aha moments, whether you had one or not. So the advantage of that task is that there's a lot of data available. This is extensively used now. And we know that it can elicit strong insights. So this is these are very powerful advantages. However, the big disadvantage is that it's pretty difficult to model this with a POMDP, with a partially observable Markov decision process. Because the structure of the task, when you need to search for a solution, this is done in your own head. This is not about a sequential decision-making task where you need to propose a solution, then you have a feedback, incorrect, correct, and then you propose another solution. That makes it difficult. Therefore, the solutions now are either we need to adapt the modeling to try to model that task, or we need to change the task. And so, of course, I've chosen the second one, and the task that I chosen to do, which you already know, is the Wisconsin card sorting task. So you probably all know how it works. You have the target cards. There are four of them. They all have symbols, and the symbols have three features: the number of symbols, the shape of the symbols, and the color of the symbols. You have the source card that you're going to have to draw from a deck, and then you need to match the source card with the correct target card according to some hidden rule that you, of course, don't know in advance. So here, if it's the shape rule, then you'll need to choose the second card. And then after X correct guesses, there is a rule change. The problem with that task is that the rules are too obvious to elicit strong insights. Shape, number, and color rules are pretty straightforward to think about. Therefore, we're going to modify it, and we're going to add a rule that is a non-obvious rule. That is here is called the exclusion rule. And the exclusion rule consists of matching the card with no same features. So here, for example, it will be the first one because the number is not the same, the shape is not the same, and the color is not the same. And of course, there will be no rule switching because that's not something that we want to test. Of course, it can be once you model the task. This is the modified Wisconsin task that we're going to use now. So how are we going to model this with a POMDP? Well, we're going to do it in the following way. So if you look on the left, you have the factor graph. This is highly classical in the active inference literature. You have the transition between hidden states, and then, of course, all the factors, which are the likelihood matrices, the transition matrices, etc. You have the expected free energy on G, you have the preferences, you have the expected precision, gamma, and then you have the policies, pi, and of course the observation O. So for the hidden states, we only model the source card because the target card actually stay the same. So we only model the source cards, and we're going to model each of their features as a separate hidden state factor. So first, you have the shape that that have four different values. You have the color, the number. You have the hidden rule. That's the hidden state that we're actually trying to infer in order to win the game. You have the task sequence. You have the viewing, response, and feedback phase. And then you have the choice, which are the four cards. And then you have the wait choice, just because it's also the undecided choice. It's just when you start the game, well, you don't choose yet the card. So in the beginning, basically the states is just the wait choice. Okay. Uh, I actually divided in task sequences mostly because I wanted to have deep policies and because I wanted to model and to simulate expected precision and update in expected precision, meaning dopamine. Then if you look at the outcome modalities, well, you have also the shape, color, and number. This is what you see. You have the choice again, so you have the observed choice, the action that you've taken, and then you have the feedback that can be incorrect, correct, or undecided when you haven't made the choice yet. Then on the right, I wanted also to show the prior over the rules. So of course you have prior over all the hidden states, but the rules are going to be the most important one because that's how I'm going to model the fact that it's not obvious. I'm going to put a lower prior on the exclusion rule and an equal prior for the shape and color and number. So this is the assumption that I'm making right now, that we can model the fact that it's not obvious by putting just a lower prior. And for those distributions, I'm going to only represent the concentration parameters. So here we're going to use Dirichlet distribution, which is usually used, and the concentration parameters are going to be the parameters of this distribution. I hope it's clear. And then once we have the model, we can, of course, simulate. This is the result of the simulation. So there's a lot of things in the slides. So let's maybe focus on the top left panel. This is the action selection. So if you look at the red markers, this is what the agent selected as action. And then the gray levels is actually the action probabilities every time that the agent, before the agent takes the action. Just below, you have the outcome, so whether it's correct or incorrect. You can see in the beginning that the agent makes a lot of mistake, of course, and progressively get it right. You see the hidden state and the posterior beliefs about the rule, the hidden rule. And you can see here that the exclusion have higher and higher probabilities until actually the game is solved. Just below, you have the precision, so you have the simulated dopamine. Of course, when the agent starts getting the rule, dopamine responses increases. And then you have several definitions of confidence. So the first one that I've used was the probability of the best policy. So the best policy here is defined as the policy that leads to a minimum of reduction, a minimum of free energy. And so here you can see that the confidence increases here gradually, because remember, we don't have any Bayesian model reduction, or rather, we don't have any insights simulated here. We have a progressive confidence increase. And then if you look at the free energy, it's a bit chaotic, but you see overall an average decrease in free energy. Then we have another definition of confidence, which is the negative entropy over policies. And you see again that it decreases a little bit in the beginning, then re-increases. And then finally, you have the precision. So this is the gamma variable. Okay, so this was, of course, without any reduction in model complexity. So the question here becomes, how can we simulate this complexity reduction? And a very natural, straightforward choice is the Bayesian model reduction. So it assumes it has really minimal assumptions, and the only thing that you need is a full model. Here I just reported the base rules for each of them, and then the reduced model. And the only difference between the two is that you have different priors, but you have the same form. And that is really important because you don't change the form when you do Bayesian model reduction. You only change the priors. You have a reduced prior. And so that's why the likelihood is the same, for example. And then from there, with a few steps of derivation, you can actually get the expression for the free energy of the reduced model. That's going to be very important because that's we will need to evaluate in order to reduce our model. Okay, so now, of course, we have a specific case. We have a discrete model and we have the Dirichlet distribution. So if you parameterize our prior, so the prior can be full or reduced, indicated by the tilde, and we have the approximate posterior, can be also full or reduced. And all of those are parameterized with Dirichlet distributions. If you have this, then you have very simple expression. You can have the concentration parameters of the reduced posteriors, that is indicated such as so. And then finally, you can have the expression for the reduction in free energy when you go from the full model to the reduced model. And it has a very, very simple expression where the B refer to a beta distribution. So now let's go a little more practical and let's see how it will look like when you actually simulate it. So let's take the first trial number 1. Here, I will only represent the prior over the hidden rules, shape, color, number, exclusion, the choice that the agent make, and then the feedback. So you can imagine that if you make the choice of picking the 4th card and the feedback is incorrect, then it's less probable that it would be the color rule, because if it was the color rule, it would have been correct. So now you go towards an update of your distribution, of your concentration parameters. And what happens is that you're going to increase the count of the shape, number, and exclusion rule, because those are the ones that are consistent with the observation. And now, and that's what is different when you want to simulate model reduction, we're going to go through a phase of reflection. So we're going to consider 4 reduced priors. What if, for the first one, the shape rule was the correct one from the beginning? It had way many more counts than the rest. And then the same thing for the color rule, same thing for the number rule, and same thing for the exclusion rule. So now the question also becomes, how can we go from the posterior to the reduced priors? Well, there's many ways of doing so. I've tried different ways, but for me, what worked the best was to actually add an artificial count that I call here p count. So it becomes a hyperparameter, and you just need to add that p count to each of the hidden rule concentration parameter, and then you have your reduced priors. Now, what is important to do is taking the previous expression of the reduction in free energy and evaluate what would be the reduction in free energy if that would be our prior, if we would have taken that prior as our prior from the beginning. And as you can see here, you already have some delta F, some difference that are negative, meaning that 3 of the reduced priors already lead to a reduction in free energy. So you can say, okay, now we can already take for example, the third reduced prior, which has the biggest reduction in free energy, and that would be our new prior. So we need to prune our model. But of course, there's a problem here. If we do that, then it means that we take the number rule as the right one, which of course we know that it's not the right one, is the exclusion rule the right one. And that's because we don't have enough evidence. This is only the beginning. So if you allow your agents to reflect and take any reduction in free energy as a potential reduced model, then it will lead to a model that is very unstable, a model that is going to prune itself anytime that there's a minimum amount of free energy reduction that can be observed. So instead, you want to build some robustness and you want to add a threshold. And you want to say, we're only going to take the reduction in free energy below a certain threshold. And now we can, for example, ignore those ones. If the threshold is low enough, we can just keep going. And let's imagine that we keep inferring, we keep playing the game, and we arrive at 1232. 1232, you have a new, of course, distribution of the concentration parameters. You make a new choice, you update, it was incorrect again, unfortunately. You update your distribution by just adding the counts. And now you also go through the reflection, once again. You go through a reflection at each trial. But this time, for example, let's imagine that the last delta F is actually below your threshold. That's perfect. It's below your threshold. And so now what you can do is you can engage in Bayesian model reduction. And you can also notice that the first 3 reduced priors lead to an increase in free energy. So it's a good thing that we didn't reduce our models from the beginning. Now let's engage in Bayesian model reduction. So there's 2 things that we need to do. We need to go from the full posterior to the reduced one, and we need to go from the full prior to the reduced prior. And how are we going to do that? Well, we're going to do that by putting all the counts that were accumulated in the other hidden rules and putting them in the exclusion rule that was the right one from the beginning. And that's how you will actually get your reduced posterior and your reduced prior. Now that you do that, you can just use those new distribution as your new distribution for the next trial. And so now you confidence, you know that the correct rule is the exclusion rule, and you can keep playing the game. And since it's the correct one, you get all correct guesses. So let's see how it looks like when you really want to simulate it with an agent. And that's what we get. So again, busy slide, my apologies. But the first 3 panels are the exact same thing as what we saw before, meaning that yeah. I thought somebody wanted to intervene. So the first 3 panels on the left, it's also the action, the outcomes, and the hidden states. And then what is very interesting is when you look, for example, at the free energy, and you see that the decrease in free energy is actually very discrete. From 1232, from 1233, this reduction in free energy is mostly caused by Bayesian model reduction, by the fact that we reduced our model. If you look at the confidence now, you see then a sharp increase in confidence that is closely related to what we saw in the trajectory of insight versus non-insight, a sharp increase versus a progressive increase. And then finally, a really nice graph that I started plotting was the expected reduction in free energy. So this is not the reduction in expected free energy. Maybe I should have phrased it better. This is the reduction in free energy that you evaluate in the reflection phase at each trial. And here, as you can see, the curve that goes below and touches the threshold is the curve that represents the free energy reduction for the exclusion rule. If you increase the count of the exclusion rule, what would be the reduction in free energy? And once it hit the threshold, immediately a Bayesian model reduction is triggered and insight is experienced. So another thing that we can do is look at the performance. What if we simulated a bunch of agents with BMR and without Bayesian model reduction? How one would actually perform with respect to the others? And so I've completely stolen those graphs from, the code of those graphs from the 2017 paper of Fritz and his colleagues, because they were very nice, but I only adapted them to my model, and that's it. So if you look here, we simulated 60 agents across 50 trials. If you look at the left panel on the top, you see the average performance where the black bars correspond to the probability of correct guesses for the agent with BMR, with Bayesian model reduction, with insights, and the agents without insight with the gray bars. And as you can see here is that you have the average performance is actually better and sooner, getting correct guesses sooner compared to actually agents without the capacity of having insights. And of course, towards the end, it converges toward probability of one because most of the agent actually just understood that the correct rule was the exclusion rule. If you look at the average free energy, so here the blue curves is the agents with insight, the red curves is without insight, and you can see that agent with insight can reduce their free energy better, most consistently, and at the end of the trial have just a lower free energy compared to the others. The average confidence here, you can see that it's higher, and even though it converges to the same value, because here is the probability of the best policy, so it converges to one, but you can see that the agents with insight actually have a sharp increase in confidence and an early increase in confidence, which is also actually what we see um, empirically. And then the last one is just a nice graph that can see all the aha moments experienced by the 60 the agents among the 60 who actually had aha moment. Then you had some agent we didn't have, and then you see all the black part is no correct guesses, incorrect guesses, and all the gray part is correct guesses. So finally, the last thing is what about fitting this model to experimental data? So there's actually been a study. I didn't choose the Wisconsin task randomly. It's because Ollinger and colleagues from the paper of 2023, what they did is that they took 78 participants, 50 ended up being solvers and 28 non-solvers, with the modified Wisconsin task that I presented you, and proved that we could elicit strong insight from them and actually made their data publicly available, which was a very good thing. So there was the choice behavior, which was the self-reported difficulty, and also the solution time. However, there's a bit of a caveat. So one drawback is that there's no measure of confidence, so we cannot confront our confidence with the empirical data. And the other one is that the proportion of insight was abnormally high. So if you actually look at the literature, usually 98% is not something that you will get. Maybe 60, 70%. This is something that Hans is more of an expert in it than me, but clearly 98% is a little bit too high. So what I decided to do was still take a few participants that I was relatively confident that they had insight or that they had non-insights, and then try to illustrate how how fitting the parameters to those data would look like. So the goal was to have two models, one model with Bayesian model reduction, one model without, and then feed them to inside participants and non-inside participants, meaning participants that didn't experience insight and participants that did experience insight during their experiments. We select the best one for each, which is done through Bayesian model selection. And then the hypothesis that I had was that models with Bayesian model reduction would fit the behavior of inside participants better than models without, and inversely for participants who didn't experience insights. I hope it's clear. So if we actually try to fit those experimental data and use the variation Laplace algorithm that is often used in that context, here we have just the selected participant. I only took 4. So of course, this is a very, very small sample. This is more of an illustration than anything else. But 2 of them experienced insight, supposedly 2 of them didn't. The number of trials, I tried to keep them high enough to avoid overfitting. And then P rule obvious is the concentration parameter for the obvious rule. This is higher, and I put them equally likely for shape, number, and color. And I put them equal to 5 for all of them. Then for the model with Bayesian model reduction, we had a few free parameters. So the first one was action precision, alpha, then the learning rate, eta, then the p-rule exclusion. So of course, this is the concentration parameter for the non-obvious rule, for the exclusion rule. And then we also had the threshold, T, for the Bayesian model reduction, and then the P count, which was, if you remember, the artificial increase of counts when you have to evaluate the different reduced priors. And so these are the results that I get from feeding those parameters. And then if you look at the model without BMR, the participants are exactly the same. I just wanted to show it again. With the model without BMR, of course, you don't have the threshold, you don't have the P count because you don't have model reduction, but you do have alpha, eta, and p-rule exclusion. And these are the parameters that are fitted. So now with those parameters, there's something that we can do is to actually try to check whether which model would fit, would explain the data better in which cases. And so what I did here, I first took the participant who did experience insights, and I evaluated two measures. The first one was the correct predicted action, the proportion of actions that were correctly predicted. And then the second one is the PXP, is the predicted exceedance probability, which is an output of the Bayesian model selection routine of the SPM package that tell you basically which model can explain the data better. And of course, here you can see that for the PXP, the BMR model supposedly is favored to explain the inside participants. But then when you look at the predicted correct actions, you can see that actually the model without BMR has more predicted action, has supposedly more accurate and higher accuracy than the other. Here, chance level is 25% because you have four choices, you have four cards. So this is a little bit of contradicting evidence, but also the PXP, this is just a weakly favoring. You have 60% against 30. It's not a clear preference. And then if you look at the non-inside participants, you can see that for the first one, it's inconclusive in terms of PXP. For the second one, clearly the first one is weakly favored. And then if you again look at the accuracy of the number of predicted correct actions, you can see that actually the model without BMR has higher accuracy. At least for the second one, the first one is really close. So what is the conclusion to that small experiment is that it's overall inconclusive. That's what I would say. And if you look at the reasons why, well, there's a few of them. So the first one is that the P count parameter is actually hard to learn. I don't exactly know why, but if you put it as a free parameter in the variational Laplace algorithm, you can see that it changes very, it has very small variation, even if you put the variance pretty high. And then if you took the threshold T, this is not learnable. I tried it, but it's probably because it's linked to a discrete phenomenon, right? Like variational Laplace needs, of course, gradients. So it needs functions to be differentiable. Therefore, it needs continuity. And that's not what we have. Bayesian model reduction is not a continuous phenomenon. And the threshold is a parameter that causes a discontinuity. Also, the fact that the inside versus non-inside feature from the study is not necessarily something that we can rely on because 98% aha moments makes you kind of second guess which are really aha and which are not aha. Here, also, we have a significantly small sample. It could be, although it's less probable, it could be that it's just due to randomness. And that if I'd actually taken a bigger sample, we wouldn't have noticed those results. And then lastly, it might be that the model is just too simplistic. I only model 4 rules, 3 obvious one and fourth one. But I mean, it also could be that there's other rules that people think about. For example, I don't know, it could be that they think about the fact that the correct card is always the left one, or the correct card is always the right one. Those rules I didn't model. And another assumption is that here I assume that the not obvious rule, the exclusion rule, was already there from the beginning, but just as I just gave it a low prior. Maybe we can think of some sort of rules that are actually being constructed across trials and constructed across the experiments, rather than a rule that was already pre-existing. And so finally, as I already mentioned in the very beginning of the presentation, this is in the context of a PhD. For the year one, what I was planning personally is to improve this model and then design the Wisconsin task with a few modifications. So first of all, to measure the confidence. So even, I mean, it could be self-reported or it could be through the cursor velocity. So apparently, when you make a choice, the velocity of your cursor, when you make that choice, is correlated with your confidence. Another thing would be to detect the trials when they are reflection, because insight is apparently supposedly linked to moments of reflection. And so if we can pick up diffused attention, for example, through EEG, then we can know which trial there were reflection and which were there were not. And then we can allow Bayesian model reduction only at those trials. Also, we can measure surprise through the proxy of pupil dilation. There's been a study that showed this. So that's also a nice measure to actually simulate and then to compare empirically. And then last but not least, it would be to have a really careful self-reported insight. So ask the question very carefully in a way that is not going to lead the participant to report a higher number of insights compared to reality. And then for the other years, I had some ideas, but it is really up to discussion. And I hope if you have some feedback or remarks, or if you have some ideas of what a really solid research plan could look like, I'll be very grateful, of course. And yeah, so this is already the end of the presentation. I would like to thank you a lot for your attention. And yeah, I hope it was fun for you to attend.
Thank you so much for your presentation. Very cool. Like lots of cool ideas there. So yeah, we usually start like the Q&A session, and in this case, like more a discussion now. So if there are like any questions or comments, please feel free. Oh, okay. So already one question. So yeah, Robert.
Sorry, that was actually an accident. I was trying to do clapping.
Okay, no
But I
worries.
will just say, just ask a question about the PhD plan actually. So where do you want to go with this? This is modeling the aha moment, but you know, by the end, is it to have found something that's like can be used, or had you thought what the end point would be?
Yeah, the goal would be to have thank you for the question, by the way, but yeah, the goal would be to have a model that's consistent with the empirical data. So that would be the goal. But of course, if we do it just with one experiment, with the Wisconsin task, for example, and we saw that it's indeed consistent with the empirical data, meaning that we can predict, for example, insight, we can predict confidence, etc., then it would mean that we have a model that is accurate enough and that can actually model insight pretty well. And then it's actually very good evidence for insight being a reduction in model complexity. So that is the goal. But of course, if we do it just with one task, this is a very short thing. This can be done in 1 year. And then the other one that I thought about was to actually model the remote associated tasks that are presented in the beginning. But this is much more difficult, of course, because it might involve some semantic network activations and other type of models that are also something that I thought about.
I see. That's really cool. I'll give it some thought for when we talk about that. And also want to say, really good presentation. I understood it.
Thank you very much, Robert. Thank you.
Yeah, I just have like a question. When you mentioned that in these tasks, sometimes they just make it adaptive in the sense that they might the rules might change over time, no? So then you have to relearn, right, and override, let's say, the kind of rule that you've learned before because now it has changed. So the prior over the set of rules should change at some point. So I wonder how would that play like with the model reduction? Because if you're like very aggressive with that, and let's say you just consider one of the hypotheses to be the only one possible, then there's no possibility for adaptation in there, right? Because no matter how much evidence you get about other hypotheses, that's going to be just discarded. So I don't know if like there are like any thoughts about that, or I don't know. I was just curious about that.
Yeah, no, that's an excellent question, excellent remark. So I don't know if you remember, but on that slide, it was this one. I've mentioned how you should be careful about putting your threshold because otherwise your model is too unstable, and you want to reduce it at any potential of reduction in free energy. I don't know if you see the trial, the slide.
Mm-hmm.
Yeah. Well, the thing here is that if you, for example, you have your threshold that is too high, meaning too close to zero, then you might go into false insights, meaning that you believe, for example, that the right rule, for example, was the number rule, but it wasn't. So for sure, it will lead to the thing here now is because you put all the others to zero and you put all the counts into only one rule. So of course now you become very confident. But also one of the fundamental characteristics of insight is this confidence. And then there's also the phenomenon of false insight where you're very confident into an idea, but it was just induced with the false insights and give you the wrong impression that is very accurate and truthful while it wasn't. So for the rule change specifically, we didn't simulate the rule change because this is something that is done originally in the Wisconsin task, but here it's modified. But of course, if you have a rule of change of rule, then what you need to do is you'll need to have many more trials because you need to have a lot of accumulation of evidence to do another Bayesian model reduction. Or what you'll need to do is you need to have not that much of a lower prior for the exclusion rule. It's a really interesting thought. I haven't done it with Bayesian model reduction, but of course you have to be careful with the threshold, with the hyperparameters that you use, such as p counts, and then yeah, it's going to take a lot of time. But of course, these are very simplistic models. It might be that in reality we have, of course, hierarchical models with many more factors, etc., that might come into play in order to change that rule. Yeah, I hope it wasn't too lengthy. I don't know if it's clear.
Yeah. No, exactly. Like I guess the hierarchy here could be the key, maybe. Like, would be like a switch from, okay, there has been a rule switch, so I have to change some kind of meta prior that I have over. Yeah.
Exactly.
So yeah. Cool.
Exactly.
Yeah. Thanks. Paul, you have a question?
Hi. Yeah, thanks for that. That was a nice presentation.
Right.
If you're trying to fit the confidence of real world, of human confidence, have you made an assumption that the confidence is the maximum probability here? You mentioned that earlier on, or does that disappear with this sort of attention mechanism? Because there's quite a lot of evidence out there that people don't actually just use the maximum probability as their measure of confidence, but it's a bit more complicated than that.
Yeah, that's a good question as well. I was kind of doubting which one to use because first of all, I've used the confidence as entropy over policies. But I realized that in the case, for example, on non-insight, the variation were very slow. So if you look here as the confidence measure as the negative entropy over policies, you see that the variation are very slow and increase very slowly. But in practice, you see a confidence measure that is a little more, that has a little higher variations, right? So it wasn't, for me, it wasn't really corresponding to what we see empirically. So I added another measure of confidence, which is the probability of best policy. But this is an open question, which one to use and which one would correspond better, the best at what we see empirically. So this is an open question. Here, for example, is the probability of the best policy. So we have this kind of gradual increase, which we also see experimentally. But again, this is open to discussion.
Yeah, there's quite a lot of, I mean, we're doing some stuff at the moment on looking at this measure of confidence and trying to tie it up with human data. So if you look at this paper by Shannon Locke, L-O-C-K-E, there's one by Lee and Ma, where they compare different measures of confidence and try and say, well, what is the sort of confidence that people would actually be using when they say the confidence? Because it seems to me if you have the wrong measure of confidence, or if you've made an assumption about a measure of confidence and then you're trying to compare that, if that's the wrong measure, then all the other work is useless, or is going to be dwarfed by the fact that you're actually using the wrong measure. But it's also possible that, you know, I feel like what you're doing is a sort of attention thing. You know, the Bayesian model reduction is getting rid of quite a lot of the possible policies, so that might correct for it. But yeah, there's a lot of stuff you can read on that, which will give you an idea of how the psychophysics people think. You know, that we as humans actually come up with a confidence measure.
Yeah, that's very interesting. I might send you an email afterwards to get the name of the papers to get more information on that.
Yeah, sure.
Thanks a lot, Paul.
Oh, Patrice, you have a question?
Hi, I'm a psychiatrist and a new learner of active inference for the last 10 years. So I want to ask you a very, very, very simple question. On this slide, upper left, card 1, 2, 3, and 4 are the different choices, either color, shape, number, correct? It's 1, 2, and 3.
No, those are actually the cards. So if you look at the Wisconsin task, you have 4 cards that are the target card, right? And
Okay.
so if you look at the 4 card above, card 1, card 3, card 2, and card 3, and card 4 are just the enumeration of those cards from the left to the right. So this is the action that I've so here, right? So you have the 4 cards here. And so
Okay.
card 1, card 2, card 3, card 4 is actually which card you're going to pick. So not which features or which rule, but it's actually which cards you're going to pick from left to right.
Okay.
Yeah.
So, okay. So Bayesian model reduction, if I can change it into language,
Yeah.
trying to learn from the conference in Oxford. That's when you have a bias prior, correct? Like that's when you introduce a bias prior into your calculation.
Yeah, the bias prior was introduced with Bayesian model reduction, but also without. So the bias prior was all the time there for all the simulations that I've showed. The only difference is that when I actually equipped the agents with Bayesian model reduction, now the agent actually can look for a reduced prior and then do that actual model reduction.
Okay, then you have to teach the undergrad what is Bayesian model reduction then? What is it literally?
Yeah, it's so this is basically here on the slide.
Yeah, it's basically there in mathematical language. Use English and explain it to me.
I'll use English to explain it to you, Patrice. Basically, Bayesian model reduction, well, it's a pruning of your model, right? So you have the full model, and what you're going to do is going to use simpler priors. So, okay, I'll use language. So, for example, here, for example, I think is the most intuitive illustration. So if you look here on the left, you have a distribution that is relatively ambiguous. You don't know which rule is going to be the right one. Then when you apply Bayesian model reduction, you put all the probability mass, in some sense, into one specific rule, saying that actually from the beginning, the right rule was the exclusion rule. And that causes a reduction in complexity because now we know that all the probability is actually just one rule. It's much simpler. So that's the model reduction part. Is the decrease of complexity of your model because now you know that the explanation is just due by this one rule, except instead of this ambiguity between multiple rules.
Okay, so this is a mathematical process.
Yeah.
All right. And when you're talking about these players in that, you're talking about a computer simulation.
Yeah. Mm-hmm.
And your point regarding Bayesian model reduction is you, I think basically at the end said somehow it's inadequate in some way.
Yeah.
Not
so
that, like there's something else that has to be considered. Can you tell me what it is?
yeah, so there's multiple hypotheses there because, well, clearly the data that I've used are only about 4 participants, which is a very small sample. So there's already a problem of the actual data that I've used. And also there's a bit of complexity when you actually add the parameters, the threshold and the additive counts, because those parameters seems to be hard to learn with the variation Laplace algorithm. So when you want to fit parameters to the experimental data, you will need to give parameters with some initial values, and then it's going to go through some iteration, and then at the end it's going to tell you these are the parameters that best fit your data. The problem is that with two of those parameters, p count and threshold, and specifically threshold, it seems like it doesn't get you the right values. It seems like it struggles to get you the values that correspond the best to the experimental data. So this is another hypothesis that could play into a role here. And also the fact that the model might be too simplistic, and maybe, yeah, and then that's it. So the actual data that I've used, the two parameters that are difficult to fit, and the fact that the model might be too simplistic.
Okay, so I've actually pulled up Carl's 2017 paper with everyone, and I get it in terms of while we're awake or while we're doing what we do, we have to rest highly on priors in order to do what we do. And the aha moments, like you said, come like when you're in the shower, when you're just like not doing what you do. And in your mathematical listing, you had the various things that affect ultimately the math problem. And I'm just gonna again speak as I usually do in these, that if you go to humans ever, the thing that I think locks people into their mathematical process of, Bayesian model, has something to do with feeling, affect, and associated response. You have it there. And this is still something that I'm pursuing, and I've talked to Carl often about, and a couple of other people. Smith and Casper Hesp and company have written an article about affect and introduced the gamma in a certain way. Okay, still haven't figured it all out, but I was looking at the math, and I'm going, well, there's that, and I know it isn't just feeling. It isn't. I'm highly simplifying it. When I sit with a patient, I treat it as just feeling, but it is one of those things that I think you also have to account for in your modeling somewhere. The human element is there in terms of how we get to where it's just, here's the model and I'm just going to work on it. And then when we're not doing that, when we're not caught up in that, the affect doesn't interfere so much. And an idea can essentially be like, oh, that's a possibility, and run down the chain. I was looking at if you go back to that one with all the one you were looking at, the one with the there. If you see and again, this is like, I know this is a computer, but at some point at trial 25, the computer tries by trial 25, it's trying all different cards, or it's just trying them and getting negative. And then soon after that comes the change in action. Again, I'm overreading something that's highly mathematical. But I would say like that's essentially like ruled out all other possibilities and tried hard enough, and it's like, okay, let's go with this one. And I don't know how you're going to model that. And if you only use a computer, you have to be very careful because, when we do have those moments, there's something else that's going on. But so just wondering about that. Thanks for the explanation of the reduction.
No worries. Thank you for your comments.
Sure.
And I think I understand the human dimension that you try try to bring forward now. And of course, this is a very very primitive form of modeling, in the sense that even the confidence that I model here is just one parameter. This is a model that is very simple. And as you already saw in the Casper and colleagues paper, is that emotions is a very complex thing. Obviously, I'm not the one who's going to tell you this, but it's, if you want, I think, to model things that are much more complex, maybe some valence, maybe some characteristic of emotion that are much more complex, you'll need to go into much more complex models as well, with hierarchies, with different precisions, and etc. So also, I think it's good to remind people that here, this is really a basic form of simulation of confidence. And yeah, and hopefully in the future we'll be able to actually model things that are a little bit more closer to people's with emotions. But yeah, anyway, thank you. Thanks for the comments.
Sure, thanks.
Cool. If there are no other questions, then we can go with you, Carl.
Is it my turn now?
Yeah, I think so.
Yeah, yes.
Very good. Right, as you've been already congratulated, that was an excellent presentation. It is extremely impressive that you've done this. When I say independently of people like us who have written the code to implement this. This is this particular application and demo of Bayesian model reduction and insight is probably one of the most complicated bits of active inference simulation in the market. And not many people have touched this since the years that it was introduced. And it is remarkable. You've got it. You've applied this to a completely different task and shown such compelling results, certainly in the numerical studies, as opposed to the computational phenotyping of the empirical choice behavior. So you should be certainly congratulated on doing this. It does serve as, I think, a very solid foundation. Well, just in, have you written this up yet? The first part?
No, not at all. Not at all.
No, I mean, it would be in itself quite a substantive contribution to the literature, just being able to naturalize all the phenomenology of insight and aha moments in computational neuroscience by appeal to active inference. That is quite remarkable. Irrespective of then how do you use this, how do you validate it with empirical data and so on and so forth, just being able to provide a formal computational first principle account of all the phenomenology of insight at its various levels, I think is very impressive. So, you should certainly think about, with your supervisors, getting this into the literature as soon as possible. That will also provide a nice foundation for the subsequent PhD thesis. So, because it was so competent, and you've clearly been deep in the issues in a way that I have not, or people like me have not, because we haven't thought about this for several years. I haven't got very much to say, so, other than well done. But what I have done is picked out a few papers that I think might be useful for you in the discussion section of the description of the current work you've just presented, but also might be relevant later on in terms of the direction of travel of the PhD thesis, and finally in addressing Patrice's question, what's the neurobiology, what's the psychology underlying this form of learning and optimization, or sense making in its broadest sense, active sense making in its broadest sense. So if you'll indulge me, what I'll do, well, perhaps could we just quickly go to your last slide with your questions, just to make sure that I've not forgotten anything that you wanted to. Right. So yeah, well, no, let's just look at that, the limitation. Yeah. Just technically, so we're just getting into the weeds now, but technically, first of all, fitting choice behavior under these insight or Bayesian model reduction schemes is notoriously very, very difficult. And exactly as you say, the reason it's difficult is that, first of all, as you note, the threshold introduces a particularly discrete flavor to the behavior that can be likened to a phase transition. That means it is sometimes quite difficult to identify when the Bayesian model reduction might have occurred, even with single subject data, and it becomes even more difficult when what you might have done is, and probably what you will want to do when you do your when you design your revised or extended Wisconsin card sort in the PhD, is just basically divide the cohort, the empirical cohort, into people with and without insight, for example, and then take the average choices or some summary of their behavior, in terms of correct versus incorrect or whatever, or reaction times, and then fit the average behavior under some idealized active inference scheme. So usually these active inference schemes are usually basically simulations of the average behavior that you would get if you had an infinite number of subjects. They can be sort of tailored to fit individual data by putting the shaky hand parameter. I think that's your alpha parameter, that sort of introduces a certain subject specific or trial specific stochasticity into the game to sort of make it fit an individual data. But really, the numerical simulations are usually regarded as the performance of the average behavior of an infinite number of people exposed to exactly the same paradigm. And of course, when you've got something that is saltatory, discrete event, it's very difficult to average something that can occur early versus late. So it's a very difficult problem. You get the same kind of problem in electrophysiological time series analysis. If things happen at different times, you can't really time not to do the averaging and to average the data in a useful way to make comparisons. So I think you're right that the nature of the belief updating implied by Bayesian model reduction and the fact that it is predicated on a discrete threshold crossing means that it's quite difficult to fit any data. And not only that, but there may be a redundancy or technically a conditional dependency between things like p count and the threshold. So increasing the p count may be equivalent to or produce the same kind of jumping to conclusions behavior, or committing to something too early than reducing the threshold, for example. And as soon as two parameters have correlated effects on the observable data, then that naturally induces conditional dependencies and makes them both very, very difficult to estimate. So normally what people do is just fix one and try to go for the other one. But I think even in your context, given what you said, the p count has very little effect on the data given everything else, and therefore you can't shift it from its prior, even if you relax the posterior variance. So that tells you it's not really estimable given these data. If you'd had confidence, perhaps, if you'd had reaction times, pupillary dilate, if you had some other data, it might have been estimable. But with these data from a single subject, it's likely it was almost impossible to identify all of these parameters because of the redundancy in terms of the effects in data space, which naturally introduce an ill-posed problem and conditional dependencies and inestimabilities. So I wouldn't worry too much about the final validation part, even to the point you might consider even suppressing that in an academic communication, or just say we will we have tried to provisionally validate this using open source data, but these data were not sufficiently informative to actually disambiguate our hypotheses in a reliable way. So we will now be looking to simpler models or more informative data. So yeah, you've basically said that in terms of the sample size being too small. I'm not so sure that's true in the sense that you've actually got quite long time series. I think though that the experimental variance in terms of a whole bunch of subjects getting an insight moment exactly halfway through the game and a whole bunch of subjects that didn't, you just don't have that. So it becomes very difficult to model that. The model might be too simplistic, and I'm thinking in terms of not the model of behavior, which certainly reproduces or everything that you might want to reproduce in terms of observable things, including sort of phasic dopamine and changes in the amplitude of simulated or synthetic evoked responses, but the model at the level of identifying when the insight occurred. So you could actually sort of think about it take an enormous amount of time, but you could, in principle, think about fitting a model where you actually introduced by hand a switch to the correct belief at each and every trial. So if you had, say, n trials, have n models, and try to estimate when there was an aha moment, or was that? Perhaps it was just a continual accumulation of beliefs with no discrete switch to the correct model. So you wouldn't actually need, or perhaps you could actually say, you could actually introduce Bayesian model reduction at successively later time points in the trial, and then you'd have n models, and then fit the n models, and then you'd have a free energy at the fitting stage, and then a softmax function will give you a probability distribution at the point at which, for this subject, the Bayesian model comparison could have occurred, and then you'd summarize that and say for this group, it occurred earlier than this group, for example, or it didn't occur at all. There was no definitive. So I think there would be ways of making your model more expressive in terms of estimating when and if the aha moment emerged. But I think it would be a lot of hard work, and well, not hard work for you, but hard work for the computer in terms of fitting hundreds of models to just one time series and then trying to integrate it. So I suspect you probably shouldn't do that for the current data, but it's something you might consider for your more finessed data, should you need to. So the question is not, is there or is there not Bayesian model reduction? The question is, when did it occur? And that's much more difficult to estimate, because that means you have to have models of the choice behavior that vary in when it occurred, which means it's not just one with and without BMR. It's BMR early, BMR intermediate, BMR late, to accommodate this sort of discrete transition from one style of belief updating or active inference to another style. I was convinced by your motivation for and the existence of a literature on this extended Wisconsin card sort. I think the whole purpose of that was to make it sufficiently difficult that there was a delayed insight. And I think if you can use paradigms that have been established in the literature just by natural selection, they usually have the kind of validity you're looking for, without wasting 2 years finding the perfect paradigm. So I would stick with that. I thought it was very nicely motivated. Your numerical simulation certainly suggests it has the right space and size to deploy empirically, and you've taken us through some of the ways in which you might want to do that. Well, in one sense, your assumption, non-obvious already there, but with low prior. Just as a generic point, when it comes to fitting choice behavior or reaction times or pupillometry data, or indeed EEG data, this fitting is always exclusively in order to find the prior beliefs that this subject brought to the table in order to best explain her behavior. And these prior beliefs can be about precisions, they can be about the structure, they can be about the number of or the number of levels in a particular state. Usually it's about precisions. So in your instance, the initial Dirichlet counts on the hypotheses is an important phenotypic characterization. That that's what I would have gone for in terms of fitting phenotyping each individual patient, subject in the open data. Is just what prior beliefs did this subject start with that best explains this subject's behavior, with or without Bayesian model selection. That would be an important parameter. Fundamental prior beliefs of that kind would be important to treat as free parameters in your computational phenotyping, and probably less the threshold T. Just as there's a little bit of practical advice. Usually, you can fix T at about 3, and I say that because that's what human beings generally do, and you can interpret that in a number of ways. So a log evidence or a free energy difference of 3 corresponds to a log odd ratios amongst your competing hypothesis of e to the power 3, which is 20, which means that basically you will require a 1 in 20 or a 95% posterior confidence before committing to a particular model. That's also expressed in statistics as a 5% nominal threshold. So wherever you look, even if you go to the Wikipedia page on the semantics, the narrative interpretations of free energy differences, which is a log base factor, you will find that 3 is very strong. So 5 is overwhelming. Sort of 2 would be strong. 1, well, it's interesting, but I wouldn't bet money on it. And 0, absolutely no bias whatsoever. So people probably use between sort of 2 and 3, as their threshold, and that's nice because you can celebrate that in your paper. This is not an arbitrary threshold. It actually has fundamental meaning in terms of being the kind of statistic which is there everywhere you look in terms of probability theory and statistics. It's effectively a log odds ratio, and very of the same kind that how many instances of heads do you need to see before you commit to the hypothesis this is a 2-head sided coin. And it's probably about 20 before you be absolute. Well, you can gauge the degree of certainty using the semantics before. The P count was yes, I can't remember the P count. I do remember worrying about that when implementing various forms of Bayesian model reduction, and it's a little bit like assuming that I've seen this once, but I could have seen it 3 or 4 times, and if I had, what effect would that have on my Bayesian model reduction? And it may, and that's why I say it may be confounded with the threshold, in the sense that if my P count is too big, I could conclude prematurely that some model is better than another model or hypothesis, simply because I made the assumption that what I've seen previously will keep on happening, and I'm not accounting the fact that there could be finite size effects, and the fact I've only seen it once actually. So I suspect that the P count and the threshold, I would just fix the P count to a sensible one, and probably one which is just what I've seen, as opposed to what I let's assume that this thing happened 5 times or 8 times, and because otherwise you will prematurely commit to a particular reduced model for any given T. Excellent. Okay, can we see your second slide? Insight versus non-insight. Oh, I see. Yes, you didn't have that. Yeah, I see. Yeah.
Yeah.
It did actually occur to me that, of course, self-reports of insight are themselves subject to a certain degree of interpretation. So I may have had no aha moment, but suddenly realize at the end I'm doing it really well. So I must have had an insight at some point, but I just can't remember what it was. So self-reporting of insight. I think you'd be much stronger ground with what you've got here in terms of measuring the subpersonal and electrophysiological or galvanic expressions of encoding of uncertainty and confidence, as opposed to metacognitive versions of confidence. That's, I think, another interesting field. Is my subjective report about the confidence or my explicit awareness of having insight in any way related to my actual belief updating, as evidenced by the physiology and the behaviours that I commit to? That's a separate and interesting question. So I very much like this sort of using pupil dilatation as a proxy for certain precisions, and I'll show you a paper in a moment that sort of suggests that that pupillary dilatation could be specifically linked to the precision of the likelihood mappings, which is great for you because there's a stepwise change in the precision of the likelihood mappings at the point of the Bayesian model, implementing the Bayesian model reduction. So that's could be particularly useful for you. The EEG correlates, likewise, you can simulate, as I'm sure you've done and know, you can simulate synthetic EEG responses. And of course, because you've got an electronic brain or a synthetic brain that could become the digital twin of a subject after the computational phenotyping, you've got lots of ERPs, synthetic ERPs everywhere. So now you can say, well, what best mixture of these synthetic ERPs best reproduces my empirically observed mixture on the scalp or source reconstructed? So now not only can you test hypotheses about the belief updating and the structure learning on the Bayesian model reduction, but you can now actually start to associate various belief updating processes at different levels during hierarchical inference with different levels in the brain through source reconstructing the EEG and see which computational sources best explain the reconstructed electrophysiological sources, and start to ask questions about the functional anatomy. If you had the EEG there, and you wouldn't be physically. I don't think you'd be physically fitting the EEG to the simulated EEG, but certainly belief-dependent amplitudes of responses, which usually mirror the degree of belief updating as measured by the KR divergence between the prior and the posterior at every belief update. So it's usually the amplitude of an ERP seems to scale with the degree of belief updating as scored by the KR divergence between what I believed before and after this next stimulus or this next saccade or this next cue. So there are all sorts of interesting KL divergences you could test as explaining condition to or trial, not trial to trial, but sort of the progression of amplitude changes in the different conditions of the extended Wisconsin card sort. Brilliant. Yeah, I think years 2 to 4, I think just doing what you've got in year 1 will take you 4 years, but we can talk about. I'm aware this is being recorded, so I'm talking quickly, so you can go back and sort of pick up the more interesting bits should you want to. Before I stop my stream of consciousness, if you indulge me, if I share the screen, I'll just take you through a couple of papers that you may find useful if you haven't already read them, that would substantiate some of the points that I've just been rehearsing. So I'm going to share my screen in the fond hope. So, do you know Vicky Victorita? Have you come across her?
No, I'm afraid I haven't. No.
Okay, well, she's actually left neuroscience now, working for the Home Office, I think, in the UK. But within the past month or so, she just handed in her PhD thesis under under Professor Rick Adams and myself, and this actually dealt with the difficult issue in part of trying to empirically fit structural learning as read as Bayesian model reduction to empirical behavior. And she actually says it is very difficult to estimate these things. But the work has been submitted for publication, but I can't find it. But that doesn't matter because her PhD is now online. And effectively, it has a nuanced version of that original rule finding, but made slightly more gamified, so that you could actually run it with real subjects. So it has a very similar spirit, but doesn't quite have the finesse of the Wisconsin card sort. But was addressing some of the issues I think your PhD will contend with. So I thought it would be useful just for you to read the final 2 chapters, just to see that she's having the same, or had the same difficulties that you were having in a related setting, and see the solutions that she found. So if you just do a Google search on this student here, or doctor now, then you should be able to get this PDF from the UCL thesis website. So that's that. Now, I repeat, I think using pupillometry is an excellent idea. There's quite a lot of literature on this. And Peter Vincent, who subsequently worked at the Sainsbury Wellcome Centre at UCL, worked with Thomas Parr and David, who became an expert on simulated hallucinations and hallucinosis and schizophrenia. But his particular focus was on active inference modeling of uncertainty read as imprecision or volatility in an evidence accumulation task, which is not so dissimilar in spirit from the Wisconsin card sort task, but was particularly interested in modeling pupil responses and using them to sort of validate both the active inference modeling, but also the use of pupillometry as measuring the precision. And I repeat, if I remember correctly, it was largely associated with the precision of, was it, perhaps it wasn't the, perhaps it was the transition matrices, but I may be wrong. So I thought that that might be a useful read for you, because it may be that you can actually augment your or read off your active inference model of the Wisconsin card sort to actually generate predictions of pupillary diameter, because this is what they did. You know, they just read off certain precisions of certain things and said, can they predict pupil dilatation? You have to put a convolution model underneath it, but in many respects, with the slow trials in the Wisconsin card sort, I don't think that should matter. So you can generalize this notion and just read up in the same way that you've read off slow changes in confidence and entropy as measures of precision. You could do that and say, are there any mixtures of precision that now predict pupil diameter, or the change in pupil diameter each trial? So you don't have to commit to a particular precision, but just say that we do believe that pupil diameter reflects noradrenergic discharge of a certain sort that in turn would reflect some kind of perceptual set that implements the precision of various probabilistic mappings in these models, and then use the time course of uncertainty or precisions in various mappings. You know, it could be the aim tensors, or it could be the transition matrices, or it could be the entropy over the posteriors over policies, for example. You've got lots of different candidates that could possibly explain fluctuations in pupillary dilatation. So I thought that might be useful in terms of making the most of the pupillometry data, in the sense that you can actually use it, generate this kind of data from your computational modeling, in addition to the choice behavior and indeed the reaction times if you had. Just thinking about the sort of the long-term, I can't remember one of your very first questions, where are you going with this? One interesting application is in the context of computational psychiatry and psychopathology, that one of the cardinal belief updating issues with people with schizophrenia is this notion of jumping to conclusions. So there's quite a large literature which you might want to refer to as a translational or clinical motivation for why you're looking at this kind of task. And just interestingly, the Wisconsin card sort task was one of the workhorses of schizophrenia research in the last century. It was one of the most sensitive tools or paradigms to what Nancy Andreasen would call score the cognitive dysmetria of schizophrenia. So there might be an interesting link here and a motivation for both formalizing and quantifying the nature of belief updating as a way of ultimately being able to characterize people with schizotypal characteristics, so that you're now looking at different. Sorry, somebody's got their hand up. I didn't notice that. Or perhaps not. Right. It just struck me, if you didn't know about this, that ultimately in 3 or 4 years' time, the people in schizophrenia research might be particularly interested in this from a number of different perspectives. So this is just a relatively not recent, but a decade old, but certainly reviewing this notion of jumping to conclusions in schizophrenia. I'm sorry, I should say that having a T that is too small will produce exactly this pathology. You prematurely commit to a particular, very precise hypothesis and thereby preclude the option to explore other ones. And then you have to go to somebody like Patrice or do psychotherapy or take certain drugs to relax those very precise priors over, to increase the latitude of the priors you can bring to the table to make your mind up more in a more protracted sense. Okay, so that was jumping to conclusions of schizophrenia. The other task that's often used, not the Wisconsin card sort, but a task which is often used to test for jumping to conclusions is the EARN task, which is, is this jar full of red beads or yellow beads, and if I draw one, how many do I draw before I say, oh, I'm committing to a red bead urn as opposed to a yellow bead urn. I'm not suggesting that you do the EARN task, but I thought you'd be interested because the EARN task has been the focus quite a lot of active inference modeling in the day, particularly by people like Tom Fitzgerald and Philip Schwarzenbeck, who unfortunately has also left academia to go into industry, but Thomas remains in academia. So I just put this up as an example of other paradigms that you could also think about generalizing to after the PhD that have relevance for this, for scoring and characterizing and quantifying the way that we accumulate evidence and learn, and indeed do our structural learning in the service of that accumulation. I just put these up basically to address Patrice's question at the end, which I'm sure you know about, but if you wanted to just answer the question, what's this Bayesian model reduction all about, sort of heuristically? Well, it's you use the word reflection, you could have used introspection, you could have used dreaming, you could have used a number of different sort of imaginal states, internal attention states, all of these states that basically pause an active interrogation of the world and just try to make sense of what you have seen. And indeed, Bayesian model reduction from a purely physiological, and neurobiological perspective was first described in detail in relation to Geoffrey Hinton's wake-sleep algorithm in this paper with Alan Hobson, who's one of the world's experts on sleep and dreaming. So it doesn't talk about, or perhaps it does talk about Bayesian model reduction. I can't quite remember, but certainly implicit is the notion of minimizing complexity as seen through the eyes of a sleep expert and through the eyes of neurobiology with all the empirical evidence. So one way of summarizing this from the point of view of a physiologist would be that the clearing one's mind is literally clearing the brain of redundant synaptic associations that can be regarded as a kind of synaptic homeostasis in the worlds of Chiara and Giulio Tononi. So the neurobiology is actually very, very simple. It's just synaptic homeostasis. It's just pruning away all those excess connections that have been accumulated during exposure to cues in the context of sleep, for example, during the day, and then reducing the complexity by eliminating those redundant connections in the right kind of way. Interestingly, the very first introduction of Bayesian model reduction, although it wasn't called that in those days, actually was literally about synaptic connections being pruned away. This was a very early paper by Stefan Keeble on applying the free energy principle, if you like, active inference, not to a person, but to a single cell, and even more than that, to a single dendrite, and asking, when and when do I not express my postsynaptic receptors? And in deciding to express them or withdraw them, that is implicit, basically, structure learning. And when do I do that? And if you work out the sort of the maths of this kind of structure learning, you end up exactly with Bayesian model reduction. So, but the nice thing here is it's all written in terms of neurophysiology. So it just takes the magic out for somebody, not for somebody asking like Patrice was for a sort of a narrative explanation, but certainly for a neurophysiologist. You can point them to this kind of work to suggest that the biophysical mechanisms of that Bayesian model reduction rule that you showed for Dirichlet counts is actually very simple and very biologically plausible, certainly in terms of pruning synaptic connections. So you can join the dots yourself, but bear in mind this was written a long time before the simplicity of Bayesian model reduction was clear in our minds, but it rests upon exactly the same idea. So that was free energy and dendritic self-organization. And it's interestingly, my colleague Takeo Isamura has taken this idea forward very recently with this archive, where he's specifically using Bayesian model reduction online, so not during sleep, but to show that you get this optimal structure learning read as synaptic pruning at a very subpersonal level. So again, this is not directly useful for your work, but it's useful references just to sort of unpack the biophysical mechanisms for those people who want to understand it at that level of detail. So that's yes, good. So those are the papers I thought you might find interesting. Is there anything that we haven't covered?
I think we have covered everything. Obviously, I will have to watch it back to get all this information, but I think in general, I don't have any specific questions. I think it's pretty clear, and the material that you shared as well is going to be very important. It's very fascinating. I think I'll have to get to read it carefully. But yeah, I think that was it.
Good.
And I want to say also, Professor Friston, I want to say that I've been following your work since over 2 years, and it's fascinating. I got into active inference because I watched a podcast where you did an appearance, and for me, it's just fascinating, that active inference. So actually, I changed the whole course of my academic life to get into active inference because I just found it was fascinating. So thank you for your appearances, and thank you for making me discover that field.
Oh, well, thank you for changing the course of your academic travails. Yes. So this is one of the most beautiful applications of active inference in this setting I've seen. So you've done extremely well to do all that. That's very impressive.
Thank you very much.
You must have been able to infer very quickly that it was important, which is good.
Yes, I did my Bayesian inference. I did my Bayesian inference. Yeah.
Cool. Thank you, Carl, as always, for your feedback, and thank you again, Joseph, for your presentation. So, as always, let's give a round of applause to Joseph. It was really nice presentation. I'm actually, like as Carl says, like very surprised. You're not even starting your PhD, and that was like really impressive. Yeah.
You guys are making me blush, but thank you.
And yeah, remind us if you could send us an email if you want the recording back.
Yes.
Just remind us and we'll share it with you.
Yes.
And yeah, I don't know, because Paul told me he might be interested. If like, do you mind sharing your slides, or you want to keep them?
No problem. Oh, sharing this. Yeah, I can send you the slide.
Yeah,
No
so in the email. Yeah, okay, perfect. Thank you.
That would be good, Youssef, because there's something that I'm doing with colleague of mine, Poppy, here, which I think may connect with your stuff. So we should have a chat.
That sounds amazing. I will send you the slide to you, Miguel, but I'll also send you an email to you, Paul, because I'm also interested in the papers that you've mentioned.
Yeah, good, cool.
Perfect.
Miguel sits next to me normally anyway, so you'll find us.
Yeah, we are in the same university. That's why. Cool. Okay, thank you so much, everyone. See you next time.
Thank you, everyone.
Thank you.